Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we are going to look at what happens when we change the coordinate system to curvilinear ones and what these equations look like and what the solution of partial differential equations actually sum up to in these cases. And so obviously we are going to start with the cylindrical coordinate system as the first orthogonal curvilinear coordinate system that is relevant to us mechanical engineers, obviously. Because as mechanical engineers, we solve many things in pipes and cylindrical coordinates. So this is modeling methods in ME. And we are going to be looking at separation of variables in cylindrical coordinate. In cylindrical coordinates. SoV in cylindrical coordinates. All right, so let's do this for the diffusion equation as we have been doing in the case of Cartesian coordinates, although the process that I'm going to follow here can be replicated for many different types of equations, including the Helmholtz equation, including the wave equation, and so on. So let's assume that now we have a case where we have also diffusion equation in terms of temperature, let's say, although it's not necessary. Another temperature is a function of R, theta, and Z, and time. So it's full, multidimensional, and transient. R, theta, Z, and time. So if we expand the Laplace operator in cylindrical coordinates, we know that that's going to look like d 1 over R ddr r dt dr plus 1 over r squared, the second derivative of t with respect to theta squared, plus the second derivative of t with respect to z squared is equal to 1 over alpha dt dt, but remember t is a function of r, theta, z, and t. And to illustrate this, the coordinate system, remember, is the z-axis, the y-axis, and the x-axis, and this would be the cylinder, so something like this. Remember the theta is measured with respect to the x-axis, and the radius or the position vector r, and this will be the corresponding z-axis. So SoV, separation of variables, applies directly as long as all boundary conditions are homogeneous and the initial condition is non-homogeneous. Also, governing equation must be homogeneous. If not, if any of these conditions does not apply, superposition can be used. Exactly the same way as we have actually used it in the previous example for Cartesian coordinates. So let's start simplifying first. This is a general case where we have r, theta, z, and t, but let's start looking at, because as opposed to what happens in Cartesian coordinates where all the space dimensions x, y, and z are the same, so having an equation that depends on x is the same thing as having an equation that depends on y. In the case of cylindrical coordinates, an equation that depends on r is completely different than an equation that depends only on z or theta, for example, because as you can see, the operator looks completely different in all three directions. So the result of the equation would actually be different. So let's start looking at problems in r and theta. These are polar coordinates. So let's look at steady problems in r and theta, in polar coordinates. In this case, the governing equation, so all we have to do is take this governing equation, eliminate the transient term, eliminate the z term, and all we have is this equation. So the governing equation looks like 1 over r ddr r dtdr, which is a function of r and theta, plus 1 over r squared, the second derivative of t with respect to theta squared, r and theta. And this is equal to 0. Where the boundary condition, no initial conditions, this is a transient, this is a steady problem. So in this case, let's assume that theta is a full circle. So we don't have boundary conditions in theta because all we have is periodicity. That means we'll explain how that works and how we can use that information to get rid of some of the constants of integration. But that essentially means that the solution at any value of theta is equal to the solution at the same value of theta plus 2 pi. So it's periodic. And also, let's say that we have at some radius b, comma theta, we have some temperature distribution, so a first kind boundary condition on the boundary, on the periphery of this polar coordinate. So this is what we have. Let's see if I can do a circle here. Not bad. And this is R. This is B. Sorry. RB. And on the periphery, we have the temperature equals to some T0 of theta. So we have some temperature distribution that depends on theta. All right, so this is a full solid circle. We'll see what happens when the circle is not solid. We have a hole in the middle. So there's boundary conditions in theta are homogeneous. There's no boundary conditions. It's just periodicity. So basically, we assume that that's a homogeneous conditions. And we have a non-homogeneous condition. So this is non-homogeneous. And this is homogeneous. Okay. So we are going to let T of r and theta be equal to r of r and theta of theta. And therefore the governing equation is going to look like, if we plug this in here, this is going to reduce to 1 over r of r, r double prime of r plus 1 over r, r prime of r plus 1 over r squared, theta double prime of theta divided by theta of theta is equal to 0. Okay. So this is just the implementation of these assumption, the separation of variables, into the governing equation. So let's bring all the r's to one side and all the thetas to the other side. So we have r squared over r of r times r double prime of r plus 1 over r prime of r is equal to minus theta double prime of theta divided by theta of theta. And as you can see, all the r's are on one side, all the thetas are on the other side. So this is equal to a constant of separation. We're going to call it lambda squared, and we are going to make it positive. So again, this could be positive or negative, and we are going to pick the positive sign. Positive because we want eigenvalue problem in theta. in the theta direction, because the problem in the theta direction, as you can see, is periodic. That means homogeneous. All right, let's continue. So theta, we solve the problem in theta. The equation that results is theta double prime of theta plus lambda squared theta of theta is equal to 0. And then the solution to this is A times the cosine of lambda theta plus B times the sine of lambda theta. We have periodic conditions, which simply means that the solution theta should be equal to the solution at theta plus 2 pi. So every full revolution should not change the solution. That's what periodicity means. So this would only be possible if lambda is integer. So basically, lambda should be equal n, which is 0, 1, all the way to infinity. So all the integer numbers, positive integer numbers. And these are the eigenvalues. So the eigenvalues are not the roots of any implicit equation. They're just simply positive integer numbers. So essentially, theta of theta is just basically A cosine of n theta plus B sine of n theta. Maintaining the frequency as integer numbers means that if we replace theta with theta plus 2 pi, we'll get exactly the same answer. So that's the eigenfunction. It's a combination of those two. In the r direction, we have this equation. R squared times r double prime of r plus r prime of r minus n squared r of r is equal to 0. Notice that I've already replaced lambda squared with n squared, because lambda is equal to n, all the integer numbers. You can identify these as the Cauchy-Euler equation. Right? So in that equation, remember, we can calculate the roots of that equation. And again, I can go through the process of solving that. We're going to try r of r is equal to r to the power of alpha. And therefore, r prime of r is equal to alpha times r alpha minus 1. And r double prime of r is equal to alpha times alpha minus 1 times r to the power of alpha minus 2. We plug that into the equation and we get r squared times alpha minus 1 r to the power of alpha minus 2 plus r times alpha times r to the alpha minus 1 minus n squared times r to the alpha should be equal to 0. So that's alpha times alpha minus 1 times r to the alpha plus alpha times r to the alpha minus n squared times r to the alpha should be equal to 0. We can take the r to the alpha as a common factor and cancel it out. And what that reduces to is alpha times alpha minus 1 plus alpha minus n squared should be equal to 0. And that is alpha squared minus alpha plus alpha. That's alpha squared minus n squared should be equal to 0. And that means then alpha is equal to plus minus n. So basically the solution will be like this. Remember, we already addressed the Cauchy-Euler equation when doing ordinary differential equations. R to the r should be equal to c times r to the n plus d times r to the minus n. So the two roots of the adjoint equation. C plus d log of r in this case is if n goes from 1 to infinity, and in this case if n is equal to 0. We have repeated roots. That leads to the logarithm. So, since t of r and theta, which is equal to r theta theta, must be finite everywhere, including at r equals 0. So we can use that as a boundary condition already to show that d should be equal to 0. Because if d is not equal to 0, then at r equals 0, this will go to infinity and this will go to minus infinity. So leading to a non-finite solution at the center of the circle, and we cannot allow that. So the solution, r of r, is equal to c times r to the n when, or if n is equal to 1 to infinity, or just simply c if n is equal to 0, which is identical. The two things are the same. That's why I use the same constant, c. So, by the way, d does not vanish if circle is hollow, as we'll see in an example next. So the solution t of r and theta, which is equal to r theta theta, is equal to the summation over all possible eigenvalues, which are essentially the integer numbers. And we are going to keep one of the constants of integration outside, c, we're going to call it a0, plus the summation from n equal 1 to infinity of an r to the n cosine of n theta plus bn r to the n sine of n theta. That is the general solution. We still need to figure out how to find those constants of integrations a and b. This is the general solution. Now, to find the constants of integration, as always, we apply non-homogeneous boundary conditions at r equal b to find an and bn for all values of n. All right, so basically that means that t at b comma theta is equal to this given value t0 of theta, which is equal to a0 plus the summation from n equal 1 to infinity of an b to the n, the cosine of n theta, plus bn b to the n, the sine of n theta. Right? And now from this, we have to extract a0, all the values of an, and all the values of bn. And to do that, we use orthogonality of the cosine of n theta, the sine of n theta, and 1. The function 1 is also orthogonal, so basically don't multiply times anything and integrate. That will get rid of an and bn, as you'll see. So, for instance, from that equation, all we need to do is, well, let's first multiply everything by 1, left and right, so it doesn't do anything. And integrate over the domain of theta, which is the integral from 0 to 2 pi of t0 theta d theta should be equal to the integral from 0 to 2 pi of a0 d theta plus the summation from n equal 1 to infinity of an bn, the integral from 0 to 2 pi of the cosine of n theta d theta plus bn b to the n integral from 0 to 2 pi sine of n theta d theta. These integral, the integral of the cosine is the sine, and when we evaluate the sine at 0 and the sine at 2 pi, we get exactly the same at 0. The integral of the sine is minus the cosine. The cosine of 0 is 1, and the cosine of 2 pi is also 1, so that goes to 0. You can see multiplying both sides by 1 will get rid of these and these, so all of these coefficients will go to 0, and basically from here we can deduce that a0 is 1 over 2 pi times the integral from 0 to 2 pi of t0 of theta d theta. That is the first constant of integration. Always easy to find. The next one, multiply left hand side and right hand side by the cosine of n theta, and then what we'll find is the an is equal to 1 over pi b to the n integral from 0 to 2 pi t0 theta times the cosine of n theta d theta, because of orthogonality. This one will go away, this one will go away, the only one that will remain is the cosine square, and there's the answer for an. Likewise, multiply and integrate. Then multiply left hand side and right hand side by the sine of n theta and integrate. And we get the n is equal to 1 over pi 0 to 2 pi t0 sine of n theta d theta. And that is the answer. Now we have the three constants of integration. We plug that in here in the general solution. Whatever condition at the periphery of the circle we have, we can explicitly find a0, an, and bn, and we have an answer for the problem. All right. So what would happen if, for example, the problem is in an annulus? Let me move to another page. So if we have an annulus, let's say that we're given this is A and this is B. So R equal A and R equal B. And let's say that for the sake of argument and illustration, remember we're going to have any kind of combination of boundary conditions inside and outside. We're going to have first kind, second kind, or third kind inside, first kind, second kind, or third kind outside. So imagine this is the pipe, this is the wall of the pipe, and then there's some fluid inside that absorbs energy by convection, and then the temperature outside is kept at a constant value, or something like that. So let's say that we have, again, the governing equation is 1 over r ddr, r dt dr. Remember, t is a function of r and theta, plus 1 over r squared, the second t d theta squared, where t is a function of r and theta. So we're still talking about a steady problem in polar coordinates. The boundary conditions, let's say in this case, the temperature at A, theta is kept at 0 degrees, and the temperature at B, theta outside is some function f of theta. Some function that depends on the angle, but it's not 0. So this is homogeneous, and this is non-homogeneous. And the problem in T at theta, or so the boundary conditions on theta, r, theta should be equal to T at r, theta plus 2 pi. And this is periodic homogeneous. Okay, we know that. So Again, we'll go through the same process. Let T of R and theta be equal to R of R, theta, and theta, plus periodicity. Whatever periodicity says. Again, you can go through the process of separating this, finding the ODEs, but the problem in theta is going to result in A cosine of n theta and B sine of n theta, such that n is equal to 0, 1, all the way to infinity. Those are the eigenvalues, and these are the eigenfunctions. And the problem in R is going to be now C times R to the n plus D times R to the minus n. So the Cauchy-Euler equation in the R direction results in this solution. C plus D times the log of R. This is if n is equal to 1 to infinity, and this is if n is equal to 0. So this is the solution in R. This is R. So basically this leads to a general solution T of R and theta that is equal to C0 plus D0 times the log of R plus the summation from n equal 1 to infinity of Cn times R to the n plus Dn times R to the minus n, there's an n here, times An times the cosine of n theta plus Bn times the sine of n theta. This is the general solution. Now we need to find all these constants of integration there. All right. So, actually, before we use the first constant of integration, we can do through the homogeneous condition. We could have done that directly here, but we can do it after the solution is assembled. So, boundary conditions. T at A comma theta is equal to 0. So inside, in the inner periphery, the temperature is 0 as given. So that means that for n equals 0, C0 plus D0 log of A is equal to 0. Then C0 is equal to minus D0 log of A. And for n greater than 0, we have Cn times A to the n plus Dn times A to the minus n is equal to 0. And therefore we have Cn should be equal to minus Dn divided by A to the 2n. By the way, we could have done this also directly here in the R solution, like we do it when we before we assemble the solution, but this works just as well. So the solution looks like D0 times the log of R divided by A plus summation from n equal 1 to infinity of R divided by A to the power of minus n minus R divided by A to the power of n times, I'm going to replace this with a new constant f instead of A, cosine of n theta plus Gn sine of n theta. And that is the new general solution. We still have to find D0, F, and G. And we do that by the same exact process that we did it in the previous example. So use non-homogeneous boundary condition and orthogonality. Orthogonality of This functions t b comma theta is equal to f of theta. So we replace the left hand side with f of theta and replace r with b everywhere, and then we'll find out that by multiplying everything times 1 and integrating between 0 to 2 pi, we'll find d0. By multiplying times the cosine of m pi and then integrate from 0 to 2 pi, we'll find fn. And by multiplying times the sine of m theta and integrate from 0 to 2 pi, we'll find gn. So d0 is equal to 1 over 2 pi log of b over a, integral from 0 to 2 pi of f of theta d theta. Then f of n is equal to 1 over pi times b over a to the power of minus n minus b over a to the power of n times the integral from 0 to 2 pi of f of theta times the cosine of n theta d theta. It's the second constant of integration. And finally, gn is equal to 1 over pi b over a to the power of minus n minus b over a to the power of n, the integral from 0 to 2 pi of f theta sine of n theta d theta. And there are the three constants of integration. All right, well, needless to say that that function f, which is the boundary condition on the outside periphery, so here we have t equals to some function of theta, and here we have t equal to 0. That needs to be a function of theta, otherwise the solution will never be a function of theta. So the only thing that drives this problem from being axisymmetric, from not being a function of theta, is the fact that the boundary condition is a function of theta. If the boundary condition is a constant, essentially just a temperature, then the solution is no longer a function of theta, and this will result into an ordinary differential equation. And you can prove that by, if you stick here a function that is not a function of theta, like a constant, then you'll get a constant out of d0, and then you get 0 here. If f of theta is a constant, then this is the integral of the cosine, which will go to 0. And this will be the integral of the sine, which is the cosine evaluated at 0 and 2 pi. They will cancel each other, and they will go to 0. So these two will go to 0, and this will simply be 1 over 2 pi log of b over a times whatever that constant value is, times 2 pi. The 2 pi and the 2 pi will cancel out. So basically, this entire portion of the solution will be 0. The solution will just simply be a function of r. If the boundary condition is not a function of theta, the solution actually boils down to just a function of r. All right. So, in addition to this, there's another type of problem that we can do in polar coordinates. It's not so obvious. Exterior problems. In polar coordinates. So this will be the case where we have, for example, a circle. Let's say the circle is of radius a. But that circle is really a hole in an otherwise infinite domain, right? And then there's some kind of condition imposed on the circle that is also a function of theta. If it weren't a function of theta, the solution would not be a function of theta. The solution would just decay in the other direction. So the governing equation for these is exactly the same, 1 over r d dr, r dt dr, which is a function of r and theta, plus 1 over r squared, the second t d theta squared r theta is equal to 0, with boundary conditions. T at a comma theta is some function of theta. Let's say some function of theta, and let's just make it 1 plus cosine of 4 theta. So let's just make it something not arbitrary for now, so we can solve this problem to a particular solution. And the other thing that we know is that t as r goes to infinity should be finite, should exist. It cannot be infinite. We don't know if it goes to 0, but we know that it's finite. It cannot be infinite. So again, we're going to let this problem it has a non-homogeneous condition, and the condition at infinity is homogeneous. And also there's periodicity, right? It's a full circle. So the solution at theta should be equal to the solution at theta plus 2 pi. So that's another condition. It's equal to r, theta, and theta. So we're going to separate the solution into r and theta. And that is going to lead to the same thing. R double prime of r divided by r of r plus 1 over r prime of r divided by r of r plus 1 over r squared, theta double prime of theta of theta should be equal to 0. That's the governing equation. And that basically means that r squared, r double prime of r divided by r of r plus r prime of r of r should be equal to minus theta double prime of theta divided by theta of theta. And those variables are separated, r and theta on either side. The only way this is possible is through a separation constant. And we're going to call that separation constant nu squared. Just pick a different name. All right. So, through the same type of arguments, the problem in theta reduces to theta double prime of theta plus nu squared theta of theta should be equal to 0. This is the right portion of this equation. This means that theta of theta is a cosine of nu theta plus b sine of nu theta. And this means that if we apply periodicity in theta, which means that the solution at theta should be equal to the solution at theta plus 2 pi, the only way that this will be possible is if its nu is an integer from 0 to infinity. Okay? So the solution in theta boils down to a cosine of n theta plus b sine of n theta. Nothing changes in the exterior problem. The solution in theta maintains the same behavior. In the r direction, let's see what happens. We have r squared times r double prime of r plus r prime of r minus n squared r of r should be equal to 0. Again, that's the Cauchy-Euler equation, whose solution should be c times r to the n plus d times r to the minus n for n going from 1 to infinity. But in the case of n equals 0, we're going to differentiate the name of the constants now. In fact, they're different. E plus f log of r for or if n is equal to 0. All right? So what we know is that the solution, one of the conditions is r, as r goes to infinity, needs to be finite. And that simply means that c is equal to 0 and f is equal to 0. Right? Remember that the log of infinite is infinite, and r to the infinite is also infinite. R to the minus anything, or I'm sorry, r to the infinite to the any number is equal to infinite, but infinite to the any negative number is equal to 0. So this goes away. This will make c equal to 0 and f equal to 0. We'll cancel out this one and this one. So basically, r of r reduces to d times r to the minus n for n greater than 0, or e for n equal to 0. So that's the solution. in the r direction. And now we can assemble the problem. So t of r and theta, which remember is r of r, theta of theta, is equal to a0 plus this summation from n equal 1 to infinity of 1 over r to the n, an cosine of n theta plus bn sine of n theta. That is the general solution. So basically nothing changed between the inner problem to the exterior problem other than these coefficient, these function needs to be r to the n, and the interior problem now is 1 over r to the n, or r to the minus n, essentially, in the interior problem and the exterior problem. All right, so we can go about imposing. So use the non-homogeneous boundary condition. Use non-homogeneous boundary condition and orthogonality. So we're told that t of a and theta is equal to 1 plus the cosine of 4 theta. That's what the temperature is around the periphery of that circle, on that hole. So that means that 1 plus the cosine of 4 theta should be equal to, if we plug that into the general solution, a0 plus the summation from n equal 1 to infinity of 1 over a to the n, an cosine of n theta plus bn sine of n theta. And we do the same thing. So we multiply both sides by 1 and integrate between 0 to 2 pi. This should get rid of these two to find a0. So a0, we already documented what a0 would be. Is 1 over 2 pi times the integral from 0 to 2 pi of the boundary condition, which is 1 plus the cosine of 4 theta d theta. So if we integrate 1, we get theta. Theta evaluated between 0 to 2 pi is 2 pi. 2 pi divided by 2 pi is 1. When we integrate the cosine of 4 theta, we get the sine of 4 theta divided by 4. And the sine of 4 theta of 0 is 0, and the sine of 4 theta at 2 pi is the sine of 8 pi, which is 0. So basically, a sub 0 is equal to 1. B over an, so basically multiply both sides by the cosine of n pi. This will get rid of these. It will get rid of these, and then we'll find an. Right? So an is equal to a to the n over pi times the integral from 0 to 2 pi of 1 plus the cosine of 4 theta times the cosine of n theta, which is the eigenfunction, d theta. All right. So that one's actually easy to do because the integral of the cosine of n theta is the sine of n theta. And if we evaluate the sine of n theta, so the first part of these is just cosine times 1. The integral of that cosine is a sine. The sine evaluated at 0 is 0. The sine evaluated at 2 pi is 0. So that goes away. Now the integral of the cosine of 4 theta times the cosine of n theta is 0 unless n is equal to 4. So basically, an is equal to 0 if n is different than 4, and is equal to a to the 4 if n is equal to 4. So all the elements, all the an's are equal to 0 except a4. That's it. That's an. And that's because the boundary condition is given in terms of a cosine. So it's an eigenfunction on itself. And then finally, bn would be a to the n over pi. Same thing. The boundary condition times the eigenfunction. And we can go over these, but the sine times 1 is the sine, the integral of the sine is the cosine evaluated at 0 is the same thing as the cosine evaluated at 2 pi, that goes away. And then the cosine of 4 theta times the sine of n theta, we can integrate that directly, and you'll get 0. It's the cosine times the sine, evaluated between 0 and 2 pi, will always integrate to 0. So, basically, if you look at the general solution here, A0 is equal to 1, Bn is equal to 0, and all the Ans are equal to 0 except when n is equal to 4. So basically, the solution, the particular solution, will be 1 plus, all the summation goes away, it will be 1, it will be An, which is a to the power of 4. So it will be a divided by r to the power of 4 times the cosine of n theta when n is equal to 4, so it's a cosine of 4 theta. That is the particular solution. And that's it. All the elements of the series go away. You can very easily verify that that is indeed the solution of this problem. You can take this and differentiate it with respect to r, multiply times r, differentiate it with respect to r, divided by r, then differentiate it with respect to theta twice, and you'll see that it matches, it satisfies the governing equation. You can also see if the solution satisfies the boundary conditions. At r equal to infinity, this goes to 0, the solution is equal to 1. The temperature is equal to 1, it's finite, 1 is a finite number. And at theta equal a, at r equal a, when r is equal to a over a to the power of 4 is 1, you get 1 plus the cosine of 4 theta, which is identical to this. So it satisfies everything. So this is what we can be confronted with when dealing with a problem in polar coordinates. This is the first of the cylindrical coordinate systems type of problem, steady state in r theta, or just simply polar coordinate type of problems. So in the next set of lectures, we'll look at what happens when we look at problems at r and z, or when we look at problems in r and when we include the time domain, Prost transient. So thank you for your attention, and I'll see you next class.